This is an NPN transistor, and the question is compute the voltage in the collector, voltage in the emitter, voltage in the base, the current in the emitter, current in the base, current in the collector, and assume beta equals 100. Now, what we'll do here is in any of these problems, just like the diode problems, we don't know a priority if, for example, the diode is conducting or not, but we'll assume it's conducting and then prove or disprove that. And then if it's not conducting, then we have to change the assumption and solve it again. In this case, we have to do something similar. We need to assume something and then solve it and see if our assumptions hold true. So here, let's just start assuming that the system or the junction transistor is in active mode, solve the problem, and verify based on the equations I wrote down earlier if it's in active mode or not. So assume BJT is in active mode, and then we will check this assumption eventually. Okay, so what I'll do is just copy this so that we can work fresh. Okay, now what I'm going to do is kind of very important, and this will make your life easy. We'll mark this up in such a way that it will make calculations very, very easy. So let's mark up all the currents in the active mode. You know, this is IC, this is B, and this is IE. That's the first thing to do. Next, we'll mark all the voltages. So let's choose another color. Okay. Remember, this is the collector junction, so this is VC. This is the base, so VB. This has the same potential. And then this point is VE. Okay, now with that, with just these things, putting the 6 numbers will make our life very easy. So now we can now start writing down equations. Okay, so first thing, instead of doing KVL and KCL, it's much easier to look at potential drop between 2 points in the circuit. So what I mean by that is, let's look at this part. This is 10 volts, this is VC. So 10 minus VC is the voltage drop across this resistor RC. So that should equal to ICRC. Okay. Then we have 4 volts and there's VB, but there's no resistor between 4 volts and VB. So there's no current or voltage drop between 4 volts and VB. So we have effectively 4 minus VB is 0, which means that we have solved for VB, it's 4. Okay, then we have VE, which is here, and this is ground. So VE minus 0 is nothing but the potential drop across RE. So it's going to be IE RE. Okay, now these equations came from effectively from a variant of KVL. Let's see what are the unknowns here. We have VC, we have IC, we have effectively solved for VB, so we don't have to worry about it. There is VE, and then there's IE. So we have the following unknowns so far: VC, IE, EE, and then IC. Okay, so there are 4 unknowns, but then we only have 1 and 2 equations. Okay, so 2 equations will not help us to solve for 4 unknowns, so we need to generate more equations. Okay, so generate more equations, we can look at what are the assumptions of active mode. In active mode, we have IB and IC greater than 0. Okay, we are going to assume that VBE is, well, it can go from 0.7 all the way, but we'll just assume that it is just 0.7. Okay, that is the voltage drop across the BE, which is the PN is 0.7. So next equation is PB. Let me separate this out. This is our equation 1. This was our second equation. Ended here. We're going to the third equation. So VB minus VE is 0.7, but luckily we know what VB is. It's 4. So we know that VB is 4 from this equation. So we can write 4 minus VE is 0.7, and this helps us to solve for VE. It's going to be 3.3 volts. Okay, so we have so far computed VB, we have computed VE. Okay, so this unknown is gone. So we still have to compute VC, IE, and IC. So we need to generate at least 3 more equations. Okay, so we're not done using all the equations for active mode. Let's go back and see what the equations are. I have not used this equation, nor have I used this equation. So let's write those 2 equations down. So we have IC is beta times IB, and then we have IE equals IC plus I. Okay, so now that I think we've got pretty much all the equations, let me just make the final countdown of all the equations unknowns. So originally we were asked to compute these things: VC, VE, VB, IC, IB, IE, out of which we were able to already solve for VE, and VB. So we have 4 unknowns, and so we need 4 equations, which I'm going to write down from here. So it says 3, this is 4. So we can write 10 minus VC equals ICRC, which is equation 1. VE equals IERE, which means that I know VE now. So I can write 3.3 equals IERE. This is my equation 2. IC equals beta IB. That's the equation 3. And then finally, IE equals IC plus IB. Okay, so fourth equation, which is just copy down of the earlier equation. So I just wanted to rewrite these so that I can now see that I only have to solve for these 4 unknowns, which are left out, but I have 4 equations, so I can solve for these 4 unknowns. So what you could do is, we can use this equation and solve for IE. Right? RE is known. RE is 3.3 kilo ohms. So IE comes out to be 1 milliamps. Once we have IE, we can use equation 3 and 4 to solve for IB and IC, because IE is known. And then we know what relation IC and IB is. So you can substitute IC over here and then solve for IB. And once you have IB, you can solve for IC. So these 2 equations give me IC equals 0.99 milliamps and IB equals 0.01 milliamps. Okay, now with those things, with those 3 things, I can now go ahead and solve for VC. I just sub in the value for IC, and RC is known. It's 0.7 kilo ohms. So VC comes out to be 5.34 volts. And this fashion, I've solved for all the unknowns, all the 6 unknowns. VE and VB were solved earlier. Okay, so with that, I have now solved the problem for all the unknowns. However, one thing which remains to be done is, remember, we had assumed this BJT to be in active mode. So we need to check the assumptions. Check assumptions of active mode. Okay, and those were IB, IC is greater than 0. That is a current flows. This is something which does show up, IB and IC, so this is checked. VBE is 0.7 volts. This is something which we assumed. We also assume that IC is beta IB, which is also an assumption. So that's an active mode assumption. So the last thing which needs to be checked is this equation. So all these things check out except for this one, which needs to be checked. VCE should be greater than 0.2. In fact, it will never be greater than VC because it's connected. The VC is the power supply on the output side. So we need to check if VC is greater than 0.2. Okay, so how do you check that? Well, VCE is VC minus VE, but VC is 5.34 and VE is 3.3. If you subtract this out, you get it as 2.04, which is greater than 0.2. So it's checked out. And this means that this BJT is actually in the active mode. Okay, so our assumption was right, and we are done solving it. Okay, now let's look at another problem. Okay, here I'm just going to modify this first problem slightly. It's not a new problem. Okay, the modification being that I'm just going to change this to 6 volts. Okay, and the question is, change the question. Here we asked, check if this, if the BJT is in active mode. Okay, for an active mode, we'll assume beta equals 100. Okay, so one change. Now, let's list the assumptions of active mode. Okay, the assumptions are IC IB is greater than 0, VBE is 0.7, VCE is greater than 0.2, and of course IC is beta times IB. Okay. Now what we do normally is, if you see the last question, this are assumed to be true, and then we only need to check if this is true. Okay, so what we need to do here is we need to be able to solve for VCE, and that's precisely what we'll do. We only write the number of equations we need to solve for VCE. Once we have solved for VCE, we check if it's 0.2 greater than 0.2. If it's not, then we know its assumption was wrong. Okay, so let's copy this. This is problem 2. Let's copy this because we're going to add a few things to it. Okay, so let's add the different currents first. I, B, I, C, I, E. Let's add the voltages. This is V, C, V, E, V, B. And as I said, we are interested very much in computing what VCE is, or VC minus VE is. So we need to compute VC and V. Let's just start writing down expression for VE. VE, which is the voltage here, minus the ground, should be equal to IE RE. Okay, so in order to solve for VE, we need IE. Let's take an equation for between involving VC and this 10. So we have 10 minus VC equals IC RC. So what we need to do here is solve for VE, solve for VC. For that, we need to solve for IE and IC, and RE and RC are known. So let's try to compute IE and IC. Okay, so to compute IE and IC, let's write down the relations we know. We know that VB, which is the voltage here, is the same as the voltage of the power supply here. So it should be 6 volts. We know that VB, which is VB minus VE, is 0.7. So we know what 6 minus what VE is. So VE is 5.3. And so by solving for VE, we don't really need this equation now because we've already solved for VE. Okay, so we are done with this. So let's just solve for VC, for which we obviously need IC. So we need another relation between IC and perhaps with something which we know. So let's look at this. We can write IC is beta times IB, and then IE equals IC plus IB. Now these two equations by themselves will not give me IC and IB because I do not know what I is. If I knew IE, then it would be very easy to solve for IC. But it seems like I do have IE here, and perhaps I can solve for IE. So though I said I don't need this equation, maybe I can use this equation because I know V to solve for IE, which will give me IE, which will come here, and then I can solve for IB and IC. So let's just do that. So let's use this equation and solve for IE. It will be VE divided by RE. VE is 5.3. RE is 3.3 times 10 raised to 3. So the IE comes out to be 1.67 milliamps. Okay. From these two, we can write IC is equal to IC plus IB equals 1.67 and IC equals beta IB. From here, what I could do is I could substitute this beta IB in this equation and solve for IC, and then I can get IB. So from here, I have IC equals 1.65 milliamps and IB equals 0.02 milliamps. Okay. However, what I was interested here was only IC, because once I have IC, I can solve for VC. So let's use this equation. So 10 minus VC is IC. IC is 1.65 into 10 raised to negative 3. RC, and RC is 4.7 kilo ohm. And so VC comes out to be 2.25. Okay, so this is VC, this is VE. So I'm going to just continue right here. So continued up there. Okay, so what I need to now do is I only need to check this assumption that it's in active mode. The assumption is I've already assumed this, use these 4 things, 1, 2, 3, 4. I only need to check if VC is greater than 0.2. So let's do that. So we know that VCE is VC minus VE. VC is 2.25 and VE is 5.3. And 2.25 minus 5.3 is approximately minus 3.05. Clearly, this is less than 0.2, which means that the condition is false. And this BJT is not in active. So that is our main conclusion, which is not in active mode. Okay, so now if it's not in active mode, we can solve it in saturation mode. So this is not part of the question, but it's actually my question number 3, which is now that we could not get this was not in active mode, can we resolve this assuming it is in saturation mode? So let's copy this question. Copy. So the question now is, compute VC, VB, VE, IC, IB, IE, assuming that the BJT is in saturation mode. Okay, and let's look at the assumptions of the saturation mode. So if you go back to here, this is the cutoff mode, this is the saturation mode. We have the following assumptions. IB is greater than 0, IC is greater than 0, VBE is greater than or equal to 0.7, and V out is VC is 0.2. Okay, so let's write this down and we'll use them. Okay, so in saturation mode, IB, IC is greater than 0, VBE is greater than or equal to 0.7, and VCE is actually equal to 0.2. And of course, IC is not equal to beta IB. Okay, we can check that, but it will not come true. So let's now reanalyze the circuit in saturation mode. Okay, let's, like before, let's put in the voltages and the currents. We have IB, IC, and IE. And then voltages are VC, VE, VB, and VE. Now let's generate, well, what the unknowns? There are 6 unknowns: VB, VC, VE, IC, IB, IE. So we better generate 6 equations. Let's just generate those equations from this figure. So looking at this figure, we have 10 minus VC equals ICRC. That's between this and this. The voltage drop between 10 and IC is the voltage drop across RC. Then we have 6 volts should be equal to VB because there's no resistor. So 6 minus VB 0. Then we have VE and 0. So VE minus 0 should be equal to IE RE. Okay, now we have to generate 3 more equations. So those would be VBE is VB minus VE equals 0.7. We also have VC is 0.2. So that would be VC minus VE is 0.2. And then the last one is IC equals IB plus IE. Okay, so 1, 2, 3, 4, 5, and 6. So 6 equations and 6 unknowns, and we can solve for the 6 unknowns. So if you solve for the 6 unknowns, you get VE equals 5.3 volts, VC is 5.5 volts, VB we already computed, that's 6 volts, IE is 1.6 milliamps, IB is 0.64 milliamps, and IC equals 0.96 milliamps. So if you check the ratio of IC divided by IB, then you'll see that it is 0.96 divided by 0.64, which is equal to 1.5. It is not nearly as close to 100. Okay, so this is typical of the saturation mode. Saturation mode, where the voltage, the ratio is not equal to beta. Okay, so this is how you solve the problem, assuming it's in the saturation mode based on those assumptions I just listed.